Welcome back from the coffee break. Hopefully that's re-energized us a little bit. And hopefully the challenge went well. If you ran into some errors and you're trying to figure it out, there are answer keys, both in R basic and in R markdown. So you can compare what you did with my answer key. And some things like the exact time you cut off each trial might not be exactly the same as what I did, but that doesn't necessarily mean you did it wrong. But it's here in case you're running into any errors and you want to go back and figure that out. We're moving into our session 3. So if you look at the materials for attendees directory, wherever you have it saved on your own computer, there is a new R basic script and R markdown script. Once again, these have the same thing. They're just different formats depending on your preference for R. If you open up R, make sure to clear your environment so you can start fresh. I'm going to open the R markdown script. We can see it says R session 3. Everyone find the files okay? Okay.
Just make a quick comment.
Yes.
One thing that I typically do when I'm like reading in files and stuff and setting directories, you can make relative directories.
Yeah.
I don't know if that's something you do, but
yeah, where you can just say jump into this folder.
yeah,
Just
put like a dot or 2 dots to indicate current directory or,
Yep.
and then everything is.
No, this is good advice to repeat for anyone online. Evgeny is pointing out that the way I write directories is the long way, and it's not entirely necessary. You can actually do cool little things with R where you tell it to, if you're in a current directory, you can tell it to jump up to a folder or backwards a folder and so on and so forth. It's very customizable indeed. If you have not installed Gazar, you will need to install it. And Gazar is a funky one. Let me open up. In the pre-workshop folder, there is an installations file that I recommend you open. This had all the installations for the workshop. And if you scroll down, before Gazar, there's a package called DevTools. This allows you to install packages directly from GitHub. So install DevTools first, and then install Gazar. And Gazar might take a little while, so get it going as soon as you are able to. Did you, oh, maybe you need to just load Gazar from library like here. You could check in packages to make sure it's showing up. Gazar isn't a CRAN one, so it could be something wonky.
No, the point is that I did my homework.
Oh, really? Yeah, I know Gazar.
Weird. Okay, a little bit of issues cropping up with Gazar. I'm going to start talking, and when we hit the Gazar functions, you can let me know if you're still struggling and we'll circle back to this. Okay, we're moving into our session 3. And you're probably thinking, Drew, we just spent an entire script pre-processing our data. How can there be more to do? I promise the pre-processing from here on is actually a lot more straightforward. That first script is just entirely because iLink has its own little ecosystem with their own types of files, and it doesn't play nice with anything outside of iLink. So that script, the entire job of it was to take iLink's proprietary file and make it something that is open source, essentially. So this next pre-processing script is more so what you'll see in methods sections of pupillometry papers, the list of operations that we apply to our pupil data, our raw pupil data, in order to do things like correct for blinking artifacts. So when we blink, our eyelid covers the pupil. We will have missing data, NAs, when there's blinking, and people will inevitably blink, even though yesterday I said in a lot of my experiments, I ask participants to reduce their blinking during critical time periods. They still blink. And in fact, I never tell them you can't blink because you don't want them to be so focused on not blinking during your experiment. That's not really the goal of the experiment. And so we expect blinking artifacts. We hope there aren't too many, because if there are too many, then we can't keep the subject in our data set because the data is going to be really crazy. So this script is going to work on identifying, correcting for blinks, and counting how much missing data there is due to blinks. So we can make an informed decision about whether this participant is one we can retain in our data set. We're going to use the same data set from the previous session. So again, this was collected by master student Jimena. And the same setup here. This is a language switching task where they're going to hear 2 sentences in a row. And without further ado, we can start to jump in. The first code chunk should be straightforward because it's the same as the last session. You can more or less copy your directories, although I will say that we are in our session 3, and the data is different in this session. You'll notice in the example data, I have a compiled folder. This is a bunch of pre-compiled CSVs. You only processed 5 in our session 2. I've put 10 here because 10 won't overdo it on your machine, I'm pretty sure. And so as much data as we can process for practice, the better. But notice these files are just like what you made. If you go back to our session 2 example data compiled, you are making these. So I've given you the compiled files, and now there are 10. I have even more if you're ambitious. This is a preliminary data set, but we have like 30 subjects of data. But for now, try it with 10, because especially like my laptop, for example, has 8 GB of RAM. And 10 is the max I could handle running on my laptop. And this is why I have to run these things on the server here at BCBL. If you want more information about how to run things on a server, don't come to me, because I really don't know. But I know just enough to log on. And I believe there are actually going to be some helpful tutorials about that for the PhD students in the fall, right?
Yeah. That's good for.
Yeah.
On the plan.
Yep.
Don't know when it's gonna happen. We ask them to do it as soon as possible.
Yeah.
I don't know.
All right. The other thing you'll see in the example data for this R session is in the pre-processed folder, there will be one file. We're going to make another one. The reason I put this one is just in case someone in the room is unable to do this first step, load 10 files at once. If you don't have enough RAM, I'll show you in just a moment how you can skip to loading this data set, and that will hopefully not break your computer. Set your directories, make sure you're sending it to the R session 3, not R session 2. So if you're copying your directories from R session 2, change 2 to 3. And also the input directory should be the folder called compiled. So compiled, and I'm going to spit things out into pre-processed. The first code chunk, let me switch back to R here. Maybe I can move this. Yeah, no, it's fine. Okay, I'm gonna run this first code chunk. Should load packages for us that we're going to need. The first code chunk, I call it aggregation. In our compiler script, we created these nice Excel-like CSV files for every single participant. But when we go to process our data from this point forward, we need all of the participants we have collected. We need them in one big file. It's going to be an enormous file. So what this chunk of code does right here is it's going to look at your directory where all of these compiled files are. It is going to, using pipes, so this is going to make it more efficient by using pipes. It's going to use this function called list apply, where essentially it's using list notation, and we're telling it to use the read_CSV function, which is a really common function in R for reading in CSV files. And we're basically saying open all files at once, as opposed to doing this one at a time. Open all files at once and make them into a list. So again, remember when we're thinking about list notation, data frames are like Excel documents. They're nice and pretty and really conceptually easy to think about. If we have a list of a bunch of Excel documents, sort of imagine two, like multi-dimensional now, it's like all of our Excel documents are lined up. This time, each of those Excel documents corresponds to a single participant. We're opening all of them at once, and it's automatically making a list in this step of this long pipe. The last step of this pipe is to use a function called bind rows. What this means is it's going to recognize that your list has all of these Excel documents, and it's going to stack them one below each other so that we end up with one really long document that goes from participant 1 to participant 2 and so on and so forth. This should be pretty efficient. Once you start to have a lot of data, it might take a while. It looks like my directories are wrong. Let's see. Oh yeah. That's so funny. Here I was telling everyone to be careful to change our session 2 to our session 3, and I did not do that. Oops. Let's try that again. What do I call you? One moment. This time. So it has already finished running this code chunk. And when you think about the amount of data you're going to be collecting, this was 10 participants. Once you have more participants, these files start to get really big, and we're making it into one enormous file, and then we are saving it. And so, like I said, if you have trouble running that step, there is already a file in the folder. Although if you successfully ran that step, you should see the timestamp is the current minute. So you have saved a new version of this file. This is a pretty efficient way to combine all of these data sets. The benefit and the reason the compiler script from the last session does it one participant at a time and keeps them separate is in case before this step, you have participants you need to exclude. So we can look at our compiled files. And this is a really easy point where if you have notes and you wrote down, participant 2 told me they don't speak Basque. They enrolled in an experiment where they're supposed to be bilingual in Spanish and Basque, but actually they don't speak Basque. They need to be excluded from this study because they did not meet the qualifications. This is a step where you could, for example, make a folder that is exclusions. You could just drag participant 2 there. Then when you run this, it'll only combine these files, so on and so forth. So this is just like a good note that you can, before this aggregation step, you can get rid of people you need to get rid of for reasons that aren't apparent from the data, because they have data. We collected pupil data, they did the experiment, but that doesn't necessarily mean they are qualified to be in this data set. So we've aggregated our file, we have saved it. If you are unable to aggregate that file, maybe because of RAM on your computer, I don't know if I don't have a screenshot of what that looks like, but usually it says like error, vector, memory, exhausted, limit reached, ? I get that a lot because I try to do things that I shouldn't be doing on my laptop. You can skip to code chunk number 3 if you need to, and you can load in the aggregated file. Even though technically the file is the same size, the process of binding all those lists together is also computationally intensive. So even if you can't run step 2, you might be able to skip to step 3, just as a note. Okay, let's move on to code chunk 4. We're going to be using a bunch of functions from the Gazar package. And this is, there's a paper, I'm sure I cited at some point, it's in the recommended readings. There's a paper for the Gazar package. It's Jason Geller and colleagues. They did an excellent job creating a much needed package. There are some little quirks to it. So for example, as I was saying earlier, some people are having a hard time loading it. It's not a CRAN like library or package. CRAN, that is the repository for R with official R packages. It is on GitHub, so you have to install it from GitHub. If you look in the installations file, you'll see that the code is slightly different for installing it. But it has a lot of really useful tools, and they've done a good job making them very efficient. One of the quirks about Gazar that is very silly is it's picky, very picky about the names of the columns in your data set. So at the end of the last step, we named our columns, and like I, for example, like to put things in uppercase, and I really liked my column names, but if I went to run the functions from Gazar on this, it would be like the function pupil does not exist, or the column pupil does not exist because mine was named pupil diameter. And it doesn't allow you to point to and say, my pupil column is called this. It doesn't let you do that. So chunk 4 is purely for Gazar. We can take a look at our data first of all. Oh, I haven't loaded my data, so I guess I should do that. Yeah, my directories are all wrong. Nope.
You put it in the big.
Load. What am I doing wrong? Why are you mad at me? This is so strange. This actually didn't even work. That is so weird. Hold for one moment while I figure out what I did wrong. File processed. Because I'm in our notebook. Just do what I want you to do. Okay. It's because I saved over it, so there's no data in it anymore. Fun, okay. Sorry. I did something wonky. I overwrote my data. Download a new copy. Why are you doing this? Sorry, I don't actually work in R Markdown very often, so I think R Markdown doesn't like the way I do my directories, just as a note. Okay, are people able to load the all data? Okay. Might just, because this is funny because in classic fashion, this worked for me when I tested yesterday, but now it's not because I'm in front of a group of 40 people. Yeah, yeah, it's just like, it's classic. I'm like sweating bullets up here and it's like, okay. So code chunk 4, pretty boring. We're renaming these columns up top are the critical ones. You have to rename. They have to be named this way or Gazar will not let you use their functions. And that's not how packages should be written, but we'll give them a pass because they made some really useful tools that we're going to take advantage of. Yeah. So if we look at all data, we have renamed our columns. So that's what the names function does. We're overwriting the header of this data frame. All right, well, let's move on. Let me go back to my slides. So code chunk number 5. This is a really common thing. Practice trials and pupillometry almost always get thrown out because, as we talked about yesterday, when you're starting a pupil experiment, there's a whole lot of orienting, a whole lot of surprise because you're trying to figure out what's going on in the task. And so that makes for very messy, noisy data. So I usually have 2, or really the number of practice trials depends on how many conditions you have. If you want to present one of each condition, for example, I might have 4 practice trials. So depending on your data set, this will be customized. The code is pretty straightforward. We are using a pipe from dplyr. So this is our pipe. And we are going to call the filter function, which is very handy dandy. We have a column called trial, and we only want trials that are 3 or above. And so if you run this and you go back to look at your data, you should see that the data starts at trial 3. Now that we've done that, just for convenience, we're going to renumber trial. We can just subtract the same number of trials we dropped. And now when we go back, it'll be back to starting from trial 1. So that's just a quick little get rid of some data we don't want. The next code chunk is we're going to start getting into the very pupillometry focused pre-processing here. This is something that actually in a lot of my papers, I did not do this step, but I have added it because I've seen it in some other recent papers, and I think it's a good pre-processing step. What this chunk does is it is looking, so in my experiments, this is also experiment dependent. Participants are looking at a fixation cross in the middle of the screen. They aren't supposed to be looking anywhere else. I have X and Y coordinates of where they're looking. And so I know if they looked way off somewhere else in the room, I know they were off task and they were not doing my task. And so I can get rid of that data. I can identify when they are not looking at my fixation cross and say that's bad data. So I have here for your reference the dimensions. This is the BCBL setup. It's going to be pretty standard across iLinks, but you should check your exact setup. And there's instructions in the manual for doing so. Our screen in pixels is 920 by 1080, wider than it is tall. That means the center is at 960 by 540. And so what I have done is I have decided on the minimum X value, the maximum X value, and same for Y, that I am going to allow to be in my data set. I give a very generous window. So I have said the middle third of the screen is okay. Anything outside of that is bad data. So that's the first thing, and you can customize these as you need for your own experiment. For example, if you're doing a visual world paradigm, these are not the dimensions you should be using to do exclusions. I'm going to go ahead and just run those. The next chunk here. This is using pipes. Once again, it's doing a series of procedures on this data set. We are using the mutate function. The mutate function can do a gazillion things. It can do so many amazing things. In this case, we are telling it to look for any cases where our X value is less than our minimum threshold outside of the area that we have said is okay, and replace the pupil value. So again, this is our pupil value. If we've determined that our X value is bad, it's in a bad zone, and we still have pupil data, we think that pupil data is bad too. And so we are overwriting it as an NA. NAs are the default that blinks are as well. And so in this way, we are essentially creating areas of missing data in the same way that blinks create areas of missing data, which means in the next steps, when we are replacing that type of missing data, we will also be replacing this type of missing data. So you can go ahead and run this. And then the next step is just a little bit of quick math so that you can report in your manuscript what percentage of data you excluded for this step. This is 6.55% of time points were excluded, were rewritten as NA. So that's code chunk 6. Any questions about that? Okay. Now we have to really get to it and start using these Gazar functions. The first of these is count missing pupil. This is the blink identification function. Go ahead and run it. It'll probably take a minute. It pretty quickly gives you some notes at the bottom of the screen. And in this case, it's telling me percent trials excluded is 0.006. Participants who need taken out, it says character 0. This means no participants need taken out. If there were participants who needed taken out, it would look a bit different. Let's talk. Oh, wait, sorry, was there a question? Yes.
On the bigger data set, is there supposed to be taken out if you did the extra files? Or do I accidentally-
Probably. Yeah, which participant is it actually?
09502.
Yep.
Sorry.
Yes.
Like, you define the threshold as 0 as 0.2, and it's what arbitrary or maybe like based on literature.
Yes. So perfect question. What does the 0.2 mean? So the missing threshold is the only setting other than we're giving it our data for this function. And I think the documentation in the Gazar article is sorely lacking. So I went into the function and I wrote up this detailed list of what exactly this function does. So the count missing pupil will look for the proportion of missing data, NAs over total observations. It calculates that per subject and separately at the same time per trial per subject. Then the same threshold for missing data is applied at that subject-wide level and the trial within subject level. So what does this mean? It means if we set the threshold to 20% and we have an entire participant who has more than 20% of their time points missing, they will be marked as needing to be excluded. If we have within a participant, maybe the participant doesn't need entirely excluded, but there could be a really bad trial. There could be a trial where we're missing half the data. It's going to flag that specific trial and say this trial needs to get tossed out. So at the same time, then this is why it's giving us these two messages here. It's telling you the percentage of trials, data set wide, that it has excluded. And it is telling you if it dropped any participants. It automatically removes these trials during this step. Yes, so that's you can see I am feeding in all data and I am reassigning it to all data. So it is overwriting all data. It has removed all of these bad eggs. Is that the expression? Yeah. Okay, a couple of important notes. Wait, is it on this slide? Maybe it's on my next slide. Yeah, okay. Couple of important notes. No, I don't know where I put this actually. Okay, here it is. The function in the notes, it reports you the proportion of trials excluded, not the percentage. So this note is wrong. It was not 0.006%. It was in fact 6%. No, 0.6%. Multiply by 100, that's the actual percentage. So this is giving you proportion. So just to know, because I've gone to report this in manuscripts and been like, wow, it's a really low proportion of stuff being excluded. It's because this is inaccurate in their notes. Okay, let's try, for learning purposes, to set our threshold lower. And sorry, I will circle back to your question, Chiara, about why it's 20. So go ahead and in the code, change from 20 to 0.05. So this is saying any participants who are missing more than 5% of their time points are going to get excluded. This would be extremely strict. Boom, look how different this is. The notes that it is spitting out, it's saying it excluded a lot more trials, first of all, because that's also like on the trial level, that's very restrictive. And it's saying I had to get rid of all of these participants. I think this is literally all of the participants. So rules or advice I have on this threshold. The 0.2 value, that number comes from Win It All's paper. It's pretty standard right now. It is completely arbitrary. And so I have a couple of important notes on this. Also, sorry, this is different than what we just processed, but this is just an example of what it could look like. A couple of notes on this. I've used 0.20 for a lot of my papers. I'm working with young adults, normal, healthy populations. If you're working with special populations, it is very justifiable to increase this number. And when I say it's arbitrary, what I mean is there is not a methodological study that has demonstrated we should be doing this amount versus that amount. They recommend the best, this Win It All paper is the one I talked about yesterday. It's the best practices paper. And they don't explain where this number comes from because there isn't a methodological study. So you can justify changing this. And the big thing that I would recommend, and actually I'm thinking about remaking this function because I think we should have different thresholds set at the trial level than the participant level. And I'm going to explain that a bit. In all of the analyses I'm doing linear mixed effects regression, and it is extremely robust against missing trial data. If you have one participant that doesn't have as many trials as the other participant, that is not going to break your model. And because that's the case, it could be very justifiable to keep participants who have lower numbers of trials. I do think within a trial, setting a lower threshold is probably a better idea because as we'll see, and I think it might be on my, let me find it. This is a visualization of what we are doing when we're identifying blinks, and we're going to be filling in areas of missing data. And so if you think about if your entire trial is full of blinks, this example is just 2 blinks back to back. If it was the entire trial, you should probably be throwing out the trial because you are extrapolating and filling in so much data that you're losing the fidelity of the original data. This is to say the 20% threshold is currently arbitrary. And particularly if you're working with special populations, you can certainly consider revising it. And I would in particular recommend it on the trial-wise level, although this function doesn't let you distinguish between the two of them. So 20% is being applied to both of these operations. Any questions about that?
Great, last question.
Mhm.
Sorry. So if I want to set, for example, different thresholds
Mhm.
for my within trial and across participants threshold, I cannot do the function.
You cannot.
I
You
have to do
could.
it manually.
What you could do, so what's the rest of this code is doing, for example, actually what I'm going to do real quick, if you set this to 0.05, it got rid of all of your participants and it overwrote all data.
Yeah.
So you should reload all data. Yep. Didn't really think that through. Hello. Yeah. You're gonna have to go back to code chunk 3. Yeah. Oh, I didn't repeat Kiara's question, but it was about what if you want to apply different to each of them? And I'll give you my advice, which I will say I haven't done this in any of my papers. I've just stuck with the 20% across the board. Like I said, I'm working with a population where if I have to throw out a participant, it is very easy to replace them.
Yeah.
And that's, very notable. There's also cases where like a data set is pre-collected. And so it's like you aren't going to be able to collect more data. Okay, so I'm rerunning this function with the higher threshold, which still is quite low, just to clarify. What do these next sections do? First of all, because I have trust issues, I like to check that I have in fact retained the number of participants that the function has told me. So this is a redundancy check. It says there are 10 participants and it had told me it didn't take anyone out, so that makes sense. If it has a list of I excluded these 3 participants, you should be able to do the math of, okay, yeah, that makes sense. But this will tell you how many participants you have left. The next thing I like to do is create a data frame for myself, back to pipes and dplyr. Hopefully you're all going to be experts with pipes by the end of this. From dplyr, I am calling some functions. We saw these at the beginning of our session 2, group by, summarize, and I'm also going to use mutate. What I am doing is I'm creating a new data frame called trial count, and this is a really nice quick summary of what I am left with after the function. So if you open it up and look at it, you'll see your 10 participants. Hardly anything was excluded here. These were just really good, not blinking young adults, apparently. There are 48 trials total. And so we can see how many trials each participant has and what percentage of trials they have remaining. So if you want to apply a different threshold at the trial level versus the participant level, you could essentially run this function on, how would you do this? You'd set it to 50%, for example. You're gonna, yeah, actually, no, the function would have to be rewritten, I think. Yeah,
You write 2 functions, one for
Yeah.
trials and one for.
yeah. Yeah, so I think it would need to be rewritten. I'll put that on my mental to-do list of things to, yeah, for my toolbox that I will hopefully eventually make.
Sorry, can I clarify something?
Yes.
When you had the trial count,
Mhm.
can you go, so if, for example, participant 7 had sort of, the proportion would be 94%, that participant would be excluded?
No,
80%.
80, yes. So
80%, that
if they,
would be gone.
so if they are, let's see what, 48 times 80. If they had 38 trials or less, they would have been excluded by the function. The other reason I like to look at this is because I have observed on occasion this function will say, I didn't need to exclude anyone. And then I'll look over here and someone will be below the threshold.
Oh.
And I don't know how that slips through. I reread the function recently when I was writing this up and it doesn't make sense for it to slip through. So I'm questioning my memory more than anything, but these 2 steps here, these are redundancy, just to make sure it is doing what it's supposed to be doing. Yeah. Okay, so we got rid of bad trials, we got rid of bad subjects. In this case, we were able to keep everyone. That's great. So we're trucking along. We have 10 subjects and we're going to move on to code chunk 8. This is where the big steps that you'll see listed in method sections are being carried out. So you can run these one at a time and watch them process. The first thing we do is called extend blink windows. Let's explain what that is. So I was saying that, so this is a graph from the Geller paper. That's the Gazar paper. It's a really nice visualization. And I think it also really conveys the story of why we need to do, what's the word I'm looking for? Extension of blink windows first. When you blink, your eyelid is quite literally covering up your pupil, but it doesn't happen instantaneously. And we're collecting at 1,000 hertz. So actually the eye tracker will collect data immediately before and after the blink when your eyelid is partially covering your pupil. And these data points are crazy. They end up looking, you know, like you can see here that there's clearly a trajectory that is very flat in this case. But because there was a blink here and the eyelid was going up and down, we're getting some pretty crazy values recorded by the eye tracker. So the solution to this is the blink windows are identified, NAs are identified, and then this window is actually made a little bit wider. We know the data right next to the blink is going to be garbage, so we get rid of it. So we extend our blinks, and then we are going to interpolate. We're going to create this line that fills in this gap. So you can start by running extend blink windows. And I want to talk through some of the settings here. This is in the GazeR paper as well. They call it fill back and fill forward, which I do think is quite intuitive. Oh, this should be 1000 Hertz. Oops. We're working at 1000 Hertz and I had it set to 500. So just to note, that was inaccurate. It's, which would mean 100. I think that means that it didn't make my window as wide as it should have. But essentially, the reason you have to put in the hertz is because if you go to your data, it's essentially, it needs to know whether if you're at 1000 Hertz, we have a time point for every millisecond. If you're at 500, it'll skip from 2000 to 998. So you'll have half as many rows is the reason we need it for this function. So this is easier to conceptualize when it's at 1000 Hertz. And the GazeR paper does clarify that this is supposed to be put in hertz, not in time bins. So we have extended the window backwards 200 milliseconds, forwards 100 milliseconds. And those are the numbers they recommend. And again, there's a little bit of arbitrariness, but I don't have any reason to find this suspect either. The next step, interpolation. If you use the function above, you need to set extend blinks to true. There's more documentation in their paper about that. We are going to do linear interpolation, and I'm going to explain what the difference between linear and cubic is. We can see that function runs very quickly, and it just gives us a little comment. There's nothing wrong. I know it's in red, so it looks like something's wrong, but it always tells you what it's doing. You actually have options though. So this is a figure 5 from their paper. Some people like to fill in missing data with straight lines. That is linear interpolation. So if you're missing data between these two spots, you draw a line between them, which is pretty easy to conceptualize. Some people like to be fancier because they know that the pupil response is curvy, and they do what's called cubic interpolation, which, as you can imagine, makes it more of a curve. Ooh. Here is my advice on this. There's no papers suggesting that one is better than the other. I've been doing linear for a long time. If there is a paper that gets published saying cubic is better for some reason, I will switch. But for now, I have just stuck with linear. There's a paper in the recommended readings. It's Matho with the hat over the O. And another one of their colleagues, and I think it's a 2022 paper. And they talk, yeah, I don't have it written here. They do talk a bit about, like, they have like a special algorithm that decides whether linear or cubic is better. And I think it's in a different package. I haven't tried it yet. So, but if you're curious and want to look into your options, there are options and different sources of advice. All right, last common standard step is smoothing. One thing I will note here, this looks a little bit, here we go. It's a little hard to see because it's a little bit cut off, but this function, here it is. Okay, this is the GazeR function. It is within many layers of tidyverse piping, so apologies if it's a little bit hard to read. But this is how, in the paper, the GazeR paper, they recommend using their functions is within the tidyverse system. What are we doing here? We are applying a smoothing function. We are quite literally going to look at the 5 time points closest to each other, and we are going to take their average, and it runs across your data set. It quite literally, if you have a slightly jagged data set, it's just going to smooth it out a little bit. And this is pretty standard. Everyone is applying smoothing, usually at 5 hertz or 10 hertz right now. Any questions about code chunk 8? This is the meat and potatoes. This is, you know, the data cleaning steps that everyone is doing in Pupillometry right now. Code chunk number 9 is also going to be very important. This is where we're going to do our baseline correction. So I, for a while, have been doing 500 millisecond baseline windows. I think my first paper, I did 1,000 milliseconds. And I feel like I've said this many times, there hasn't been like a very thorough comparison across studies, unfortunately. The baseline window, as a reminder, is we have the onset of our stimulus, and that's going to evoke a response. We're going to look at the size of the pupil immediately before that stimulus to figure out what size the pupil was before the stimulus. We're then going to take that value and we are going to subtract it. So the method I've selected here is subtraction from the rest of the trial. And what this does is when you're picturing a pupillometry plot, and I don't think I have one nearby, so let me skip to one. Oh, this is not the prettiest plot ever. But in theory, what it does is it makes your y-axis go from 0. This is how you make your value a change value. Because I do subtractive baselining, this is the increase in units. These are the I-links, arbitrary units, not millimeters here. Some people prefer what is called proportional baselining. And I'm going to refer you to the Geller paper to sort of look into what the difference is. But what I want you to imagine is this y-axis, instead of going from 0 to 60, it would be a percentage. It's a percentage change from whatever size it was here. That doesn't mean this will go up to 100. This just means it'll probably go up to like 15%. So your pupil has increased in size maybe about 15%. I think we're coming up on lunchtime. We have a lot of time for lunch, so I'm gonna keep you here for a little bit longer. Okay, so this is what baselining does. This is, we're feeding in the data set from the previous step where we got our rolling, our smoothed data. We're telling it, this is the column, and this is exactly how they do it in the Gazar paper. To specify our baseline window. So in the data set we processed, I actually took 1,000 milliseconds. So if you want, you're more than welcome to go through this script and try out different ones and see how the data looks different. The reason I've been doing 500 for quite a while is because the standard when I started was 1,000. But your data doesn't get lined up as well when you have that big of a window. So people started doing 500, including me. I have seen people moving to 250. And so there are trade-offs here in terms of the smaller your window, you could have extraneous values that didn't get cleaned up well, that could really throw off your baseline. But that being said, the closer you are to your stimulus, the more precisely aligned to 0 your data is going to be. So for example, I want my data to be as close to starting at 0 at the onset of my stimulus as possible. Any questions about baselining? That's code chunk number 9. If you wanted to try proportional, I believe it's prop is the method you would choose. And I have a feeling that, so I do have this written somewhere. I use subtractive based on, there's a paper by Riley et al., 2019, I believe. And they argue that we should use subtractive baselining, and they do a bunch of physiological investigations to justify subtractive. That is why I've been using subtractive. I have a feeling, because some people really like proportional, that there's probably going to be a more thorough methods investigation that comes out in the coming years. I know other people who do pupillometry who are plagued by this in the back of their minds and want to know the answer of which is better. So just a heads up that the times may be a changing, and I am I'm not certain which way it'll go. Okay, chunk number 10. It is now time to time bin our data. I talked a little bit yesterday about how there is such a thing as too much data, actually. It can be bad for our mixed effects modeling. It can it can inflate our type 1 error rates if we have too much data, actually. And I'm going to refer you to the I've been saying Riege, but I believe I'm pronouncing that wrong. The Van Riege et al. Paper from 2019. They go into more detail about how having too much data could be bad. So what we do is we bin our data. Long story short, this is collected at 1,000 hertz, and I want to change it to 50 hertz. 50 hertz means I will have 20 millisecond long time bins. So it'll go from 0 to 20 to 40. So if you're picturing it on a plot, instead of having 0 through 20, all of these dots, it'll go 0, 20. Don't stress too much about this. Oh, one note, the Gazar binning function has not been working for a while. So I rewrote it here. I wanted to give them credit because I just took their code and I don't remember what was wrong with it, but something is wrong with it. So if you look in the Gazar paper and in the package that you have installed, you'll see that there's a binning function, but don't use it because it won't work. For your individual data set, you'll need to customize this. So I'm grabbing the columns that I want to keep in my data set here. This is not a Gazar thing. This is a standard how to use pipes with the group by function. I'm then summarizing my data. I'm creating a new column called pupil binned. So if you think about it, we are going to take time points 1 through 20, and we're going to make it into one time point. Well, the pupil was changing in size over that 20 milliseconds. So we need to take the mean, and that becomes our new time point 20. Does that make sense? So that is what the binning is doing. And so that's why we are taking the mean of, this is our most recent pupil value from the most recent data frame that we made in the last step when we baseline corrected. So this stands for baseline corrected pupil. I didn't choose these names, so I'm sorry if they aren't intuitive. They're from the Gazar package. I'm also taking the mean of the X and Y coordinates. If you aren't doing anything with gaze, we've already excluded people who weren't looking at the center of the screen, so you do not have to keep this if you don't care about X and Y. But I wanted to put this here so that people who are doing the simultaneous eye tracking will know how to retain that data in their data set. So you can go ahead and run this. Oh, I don't think I ran my last step, did I? Oh, I haven't run a few steps, it looks like. Okay, I'll catch up with you all. There are some notes that pop up when you baseline your data. You can see that when it says join by subject trial, this is the way we baseline is we do it on a by trial basis. And that is important because things change over the course of the experiment. And so every trial is a little bit unique as far as what the size of the pupil was immediately before the trial. Now we can run code chunk 10. And what I want you to do after you run code chunk 10 to just really solidify what we are doing here, like conceptualization, is open the data frame that it's making. Mine's still running actually, so give it a second.
Which would be binned full data.
Yes. Huh, is it taking this long for other people? Okay. Yeah, that warning is fine. Okay. Wait. Binned all data. I opened the wrong thing and I had like a mini panic that it didn't work. Okay, these columns are not in an intuitive order, but if we scroll over, time bins is to the right. Looky here. Oh, hold on. Before we look at it, wait. Oh, I just realized that I have the same code chunk twice in here. That's sort of funny. I'll edit that later. Let's go ahead and what did I do? Sorry, let me do a quick sanity check. I have subject, trial. I'm gonna add a little bit to this code because I skipped a step. Select columns, we want to keep them. Okay, so our binned all data has a bunch of columns and they're in wrong order is perhaps not the right word, but for my brain, it feels like the wrong order. So I'm going to take binned all data and I'm going to overwrite it. I'm going to use a pipe. So I'm taking binned all data and I'm feeding it into a pipe from the dplyr package. So I'm calling that package. I'm going to call the function select. And I am just going to type the columns I want in the order I want, and you do not need quotes. So I wanted to go subject, trial. Then I wanted to do time, so it'll be time bins. Then what do I want next? We'll do condition, time bins. Oh, you know what? Here, we'll put pupil binned here. Condition, yada, yada. Anything else that you want to retain in the data set should also go here. I'm going to skip some things. If you run this, what you will see is our binned data set, when you go back to it, will only have the columns that you want it to have, and it'll put them in the order that you want them to have them too. This is also a good reminder that these data sets get really big, so drop any columns you don't need. And apologies, I forgot that step. So if you then want to, because we're done with Gazar, so we don't have to do their arguably silly naming. We can rename our header however we so please. So that's what I was doing in this step, but I now have I have selected different columns, so you could customize this here. So for example, I'm going to say subject trial. I need to put time next. Be careful not to overwrite your columns incorrectly. And there might be a more efficient way to do this. So apologies if some of you are cringing at my method, but old habits die hard. So I just renamed it. So if I look at binned all data, now they have nice, pretty names that I like much more. And then we save it. And this is what I like to call my all, or sometimes I name it after my experiment. In this case, I just called it all data because we aren't working on like a specific experiment for the workshop. I like to call it pre-processed. It's going to spit it out into the same folder where aggregated was. Oh, or in the wrong place entirely because I didn't change my directory, but you should get a file. This is all of the data we have pre-processed. All of our participants are in here. And then because I would feel entirely too sad if we left this session without having seen the data. I mean, we have to look at the data. We've done all this work with our code. We should at least have the benefit of getting to see a pretty plot. So you'll see that code chunk 12 has some more code. Some of it is prep where like I wanted to rename some of my columns and yada yada. And actually I dropped some of my columns, classic. This is why you don't change things on the spot. Okay. I'm gonna skip some of the code I wrote up here because it's perhaps irrelevant. But you can try plotting it. Ooh, I don't have two conditions here because I redid things on the fly and I shouldn't have, but oh well. Quick sneak peek of this data. One thing I'll note, because we're going to work with this data set some more, when you only have 10 participants, it looks sort of weird, to be honest. So if you ran more participants, your plot might look different. And in fact, because they're listening to 2 sentences, it really should be 2 peaks. So yeah, don't read too far into these 10 people that we processed. I see a question on I can see it on your face that you want to ask a question. No, it's good.
I have a question regarding right. Okay, so I don't know why in my head it makes sense. So it's like 9,800. I don't know what it is. And then it goes 9,000. No, sorry, 9,080. And then it goes 9,000.
Yeah, so this is.
And then 9,000 again. And I don't know, like in my head, this number means that it's one beam, right?
Yeah.
So they should be blocked.
An excellent point. Yeah, I didn't do it right. Oh, man. That might explain why things were being weird. Let me go back. Let me reprocess binge data. Time bins. This is what it should look like. Yeah, I don't know. It's not just you because mine also looked weird. So that's so weird. I don't know. I didn't do anything different. I just reran it. But this is what your time bin should look like. It should be skipping every 20, should start at -2,000 for this data set. I know we were doing -1,000 in the previous data set, but this one has a little more data before the 0 point.
Okay, so what is doing actually, I think I didn't understand really well, sorry.
No, it's okay. So, we have told it that we want 20 millisecond time bins.
Yeah.
Actually, if we back up a step, if we don't run the second part of this, if we just run the first part, this is sort of like stage 1. If we take a look, what it has done is it has added a column where it is labeling. So these first 20 time points are going to become -2,000. So it's actually -2,000 to -990. So you can see exactly which time points are getting brought together as a mean. Does that make sense?
Yeah.
Yeah, and so it's like the first step is to add this on the right, and then the second step is to actually recombine the data. Oh, you know what I bet it is? Hold on. Yeah, okay, so I tried at the last minute to add the X and Y's for people, and I think I did it wrong. Yeah, okay. So what I just did there. Yeah, if you get rid of the X and Y means, I added this like days before the workshop and I probably didn't double check that I did it correctly, but delete this and run it again and it should be better this time. I don't know why. Maybe Daphne and I will look at it later and I'll think about why it's. Yeah, so I don't know, but I probably just made some wrong assumption about how to write the pipe.
Yeah, now it's right.
Yep, okay. So
What is when it's averaging across the 20 time points to create just one beam.
Yeah.
Okay.
Yep.
Can you show again the renaming?
Yeah. Oh yeah, I guess I have to back up if I'm gonna do that, but. So if you just run this chunk. And actually it sort of looks like, so this is -990. So the first spin is actually not 20 units being taken as a mean. So small note that your first time point is actually a 10 millisecond bin, which I've never noticed before, but The good news is we don't actually analyze the data from here. So if it starts on sort of a half the size bin that it should, it won't break things. So we can see the negative 1980 goes for 20 rows. Does that make sense, Sandy?
Mine looks different, and I don't know, but it just potentially just mine. I don't know why I'm not enough. It's bidding and maybe I've run something.
Yeah, I don't know. This is what the quick plot should look like. If you delete the X and Y thing, it'll probably turn out like this time. To wrap up, so that we can go enjoy a lovely lunch together. This is the real meat and potatoes pre-processing. You are all troopers this morning for turning iLinks files into something intuitive. That part was it's sort of a thankless process. This part, we've actually taken our data and done really cool stuff. We've cleaned it up. So what did we do? We took all of our individual subject CSVs and we put it into one giant file. And then we started using functions from the Gazar package to correct blinking artifacts. We also baselined by trial and subject here so that when we make plots like this one, they will start from 0. Small note, if you care about baseline values or you care about the general size of the pupil and not just the change in pupil, you want to get that data before you apply that baselining stuff. And I have done that in some papers. I am interested in the size of the pupil to sort of look at what's called tonic arousal as opposed to this phasic pupil response.